Hello everyone. In the previous video, we introduced Meta's new open source large language model called Llama 3. Specifically, we showed how to use the Llama 3 model with 3 billion parameters, fine-tuned to instruction, so the instruct version, to do sentiment analysis of financial text. We showed things like if you have like some sort of text like Tesla cuts Model Y prices in China by X, then it will respond with things like this is bearish because price cuts will cut into margins and that sort of thing. Occasionally you get weird answers like it's bullish because it'll generate more sales. So it's not always perfect. And we said also that like if we want just a one-word classification, bearish, bullish, or neutral, then at the end we can say respond in one word. And the 8 billion parameter model amazingly handled that. So that was really impressive. So in this video, what we're going to do is we are going to actually try to go one step further and fine-tune this model to a sentiment analysis data set of Tesla, which has basically a bunch of summaries and a label of bearish, bullish, or neutral. This data set was derived from AlphaVantage. I can show you how to get it. So anyways, we're going to show you how to fine-tune the model specifically for the text classification problem and sentiment analysis. If this video helps you at all, please like, comment, and subscribe. It does help a lot, and I appreciate it. Thank you so much. Okay, so let's get started. This notebook will be available, so you don't have to look too hard at everything. So the first thing that is important is you need a GPU. So if you do runtime managed sessions, you need to have a GPU. So like as you see, oops, why am I using a GPU here? Okay, so you do runtime, change runtime type, and select the GPU. Since so the free version, the GPU you can't use for so long, but if you have the paid version, and I honestly just paid, so I might even have access to this super duper GPU, but soon I won't have access to it. But anyways, you need a GPU. I'm going to use the L4 for now. I don't need the A100 at the moment. Okay, so basically, just real quick, let me do some installs. You should use the latest version of Transformers, and then you need like data sets, accelerate, evaluate, bits and bytes, Hugging Face. All these things will be in the notebook. Okay. So what is the big picture of fine-tuning? So remember, I spoke about this in other videos, that the big picture is with fine-tuning is you train a model, like there's a pre-trained model that's trained on the entire internet, on like so much crap, it's insane. Like it requires so much compute power, so much GPUs, billions of dollars of GPUs, maybe not billions, but millions and millions, maybe hundreds of millions. An entire internet. It requires so much compute. But then you get like this like super knowledgeable model. But the model is not that useful. It's basically a document completer of the internet. And then you fine tune it to specific tasks. So in the case of ChatGPT and Llama 3, you would fine tune it into like an instruction or assistant type data set where you have like sort of these assistant dialogues that go back and forth, right? So that's the big picture of fine-tuning. So for our specific case, we're going to fine-tune it on sentiment analysis task. So specifically, we're going to do something called parameter-efficient fine-tuning. So what is parameter-efficient fine-tuning? So the big picture is, as I said before, the model is huge. So like normal people like us, we can't really like fit the model in normal GPU memories and that sort of thing. So there are these like really cool ways to fine-tune models in a parameter-efficient way, which requires way less memory, and it's much faster and way less parameters. So let me explain the two biggest components. So one is called LoRa. So LoRa is a way to what happens with LoRa. It stands for low rank adaptation, low order rank adaptation. So what happens is when we're fine-tuning, we're going to keep the original weights. We have our pre-trained model weights. But when we're updating our model, we're going to learn a low-rank approximation to update the model. So like let's say our model in theory is like 1 million by 1 million parameters. So like that's so much. Instead of updating a million by a million, we're gonna update just a low rank approximation. Let's say, for simplicity's sake, a million by 10 times 10 by a million. So we need to now update just these two matrices of a million by 10, which is 10 million, and 10 by a million, which is another 10 million. So 20 million parameters as opposed to a million squared, which is God knows how much. So this really, really, really reduces the amount of parameters to update and has good properties. It tends to do very well. So that's LoRa. So these, by the way, these matrices that you're adding to your model are known as adapters. And you can merge them back into your weights later on if you want. But this is not to get into the fine details of the method. This is just to give you an overview. Okay, so the other thing we're going to use is called QLoRA. So not just are we going to do this LoRa part, we're going to also quantize our pre-trained model. So QLoRA will quantize it to 4 bits, and it has all these other like unique optimizations. Uses something called normal float, double quantization, page optimizers. I don't want to get into details, but like it does add another level of compression and stuff like that. Okay, so now that I gave you the big picture, and if you guys are interested in seeing these in details, leave a few comments and I will actually go over it in details. So the big picture is when we want to fine tune for sentiment analysis classification, we can do two things. We can either do what we did in the previous video, where we kind of gave the model like sort of a prompt where like, okay, like you can classify sentiment as bearish, bullish, or neutral, and then at the end it'll give you the answer. So basically it'll be something like Tesla slashes Model Y prices, and then we can have like this big imaginary equal sign equals bearish. So like the model will learn like to give you a response in this format. And then at the end, as a second step, we can remove the bearishness. The benefit of this is just because these models are kind of like maybe a little bit more optimized for text generation, but like it's not really the most natural way. What the most natural way is to add some sort of like classification head at the end, which means basically like it's like you have the llama transformer. Again, I won't go into details about it. And at the end, you have you add to the last non-padding token a linear head, which will then predict three labels in our case: positive, bearish, or neutral. And I'll show you guys in a bit how this looks like. So this is what we're going to actually do in this video. We're going to do we're going to add the sequence head. We're going to add an extra layer that will have the positive, bearish, or neutral. And I'll show you how it looks. So, okay, so let's see. We already installed these things, so we have to restart because the accelerate thing needs restart. So let's restart session. Okay, so now before we get started, let's just talk a little bit about a few more things. So we talked about how we're using the parameter efficient fine tuning. So the LoRa and QLoRA. So we need a config for each one. So for the QLoRA, the quantization, you have what's called a bytes and bits config. And for LoRa, you have a LoRa config. You need these two things for the parameter efficient fine tuning. Oh, and sorry, if I wasn't clear above, the classification head, the input would be like the sentence Tesla slashes Model Y prices, and the output would just be bearish, bullish, or neutral. So 3 outputs. And sorry if I said it twice, I'm all over the place. Anyways, okay. So so we need the 2 configs, one for the quantization, the bits and bytes, and one for the LoRa. Okay, right. Okay. So now I wanted to say that Hugging Face makes fine tuning very easy. There's like this trainer class that could do everything for you. So the main components is like you need a data set, a Hugging Face type data set with train and eval, and I'll show you how to get that. Something called a data collator, which does the like batching and tokenizing and that sort of thing. You need compute metrics, which will basically log metrics every epoch that's finished in the fine tuning. And in our case, because we have a custom trainer, we'll have a custom loss function with class weights. And then there's all these other parameters. They're called training arguments. Maybe I'll write it here. Training arguments. Like epochs, like num epochs, learning rate, weight decay, etc. So like there's a lot of things you can configure, but that's the big picture of what you need. Okay, so like in the previous video, you have to like log into Hugging Face. You have to put your token for the Llama 2. And again, if you've never used it, you're gonna get an error the first time you run the Llama 2 model, and then you're gonna sign up and eventually you're gonna get it. Anyways, okay, so now now we're finally ready to do the notebook. So let's do our imports. Okay, so we are going to be working on the Tesla sentiment analysis data set, which was derived from Alpha Vantage. One second, sorry. Okay, so let's add the data set. We'll add it here. And then we're going to wait until it's done. And then once this is done, we are going to load the data set. So we are going to do basically read CSV, Tesla sentiment.csv. As you see, the data set looks like this. We have the time the article is published, the summary, and the label, bearish, bullish, or neutral. Because we're going to do fine tuning, and fine tuning, like these neural networks do not know about like about like stringed labels. We're going to have to turn them into like numerics. So we can do this like thing where we can do as type category. So now we have df label equals df label dot as type category, and it'll look the same. And it'll look the same. But then when you do, sorry, let me just run it and show you guys. Okay, so when you do df label dot as type category, it looks the same, but the category has a code. The code would be like 0, 1, and 2. So if you do .cat.codes, you get 0, 1, and 2. And I'm just showing you the first few elements. So bearish would be mapped to 0, neutral would be mapped to 2, and then a bullish would be mapped to 1. Eventually, we might want to decode it. So if you look at it here, like if you do df label.cat.categories, you'll see that you have bearish, bullish, and neutral. So we can create this like category map, which will go from like code to category. It will be like 0 to bearish, 1 to bullish, 2 to neutral. As you see, 0 bearish, 1 to bullish, 2 neutral. Okay, so that's going to be used later just to show the results in like a little more human-friendly way. Okay, so we're going to split the data set into train, val, and test. Again, a lot of people I see do this like stratified split, where they split based on the class weights proportion, because the classes are slightly imbalanced. But I think that's not as good in our case, because you'll see that many articles around the same time are very similar. So it's kind of like if you do it that way, you're going to have like some sort of leakage issues, because you can have like 2 articles that are like very close in time that could be very similar topic in the train and the test set. So we're going to actually split across time. First 60% is train, next 20% is val, and the last 20% is test. So we're going to do this like dot shape 0, dot 60. This gives us the first 60%, and then times 0.8, first 80%. And then we can go like this with the log to get it, and we see we get a training set of size 3508 and a val and test of size 1170. Okay. So now we're going to need to convert the pandas data frame to Hugging Face data set, and then after I'm going to want to shuffle the training set because that helps a little bit with performance, and then I'm going to want to put the data set in a form where it has like, it's like a dict form where it has like train, val, and test. And then after, I'll show you, we're going to need to make a tokenized data set of this. So first step is the dataset.fromPandas to make the data set for train, val, and test. The from pandas turns the pandas data frame into Hugging Face data set. Note I dropped the label thing. The label was the string version of bearish, bullish, and neutral. And remember, I had the target that was the int version. So I'm going to drop it because later I'm going to actually rename the target to label, and I don't want any issues with that. So let's do this first step. Okay, the second step, like I said, is we're going to shuffle it. I'm going to do set seed for reproducibility. So I'm going to do dot shuffle seed equals 42. Okay, so then, like I said, we're going to combine into single dict data set. So we're going to have train, val, and test. And I'm going to show you how this looks like. I'm going to write data set. Maybe I'll write data set. So it looks like this. You'll have the train, and then the train is a Hugging Face data set. Val is a Hugging Face data set. Test is a Hugging Face data set. So if you do data set, you can do data. Oh, wow, I have this cool autocomplete train. I guess that's what you get when you pay. And so you see this is the training data set. This is not a video on data sets, so I'm going to go fast through this. Okay. So one more thing is like the classes are not so balanced. So let's do an inverse of the class of the distribution of the labels as class weights. So let's look at the distribution over the labels by doing value counts. So you see that like label 2 has 45%, label 1 has 30%, label 0 has half of label 2 even. Let's now do the inverse of that. So we'll do 1 divided by this to get class weights. And I just kind of like, so step by step I do 1 divided by this. So this gives you like inversely proportional to how often it is. And then I create a PyTorch tensor because we're going to need it in that format. And then I normalize it by the sum, so then the class weights would add to 1. And as you see, these three things, 0.4 plus 0.3 plus this, add to about 1. Okay, so now that we have the data set out of the way, minus the tokenization part of the data set, let's load the LLama model with 4-bit quantization. These are the QLoRA things, and all those are in the bits and bytes config. So first of all, let's specify the model name. The model name is from the Hugging Face hub, Meta Llama 3.3b. We're not using the instruct because as Meta recommends, you should use the base model when you're fine tuning. Now we have to add the quantization config for QLoRA, which is basically has the load in 4-bit equals true. BNB 4-bit quantization type. This is normal for float 4. Double quantization, and then compute type is B float 16. That's brain float 16. And then we're going to do it similarly, add the LoRa config. I'm going to rush through this. Basically, this is the rank. Remember in my example, I had like 1,000,000 by 10 times 10 by 1,000,000. So the rank would have been 10 in that case. R would be 10. But here it's 16. Alpha is a measure of the trade-off like between like the pre-trained weights and the new weights. And target models is what to apply LoRa to. Dropout is like to prevent overfitting, where to drop out from the LoRa layers. And then there's all these other things like this task type sequence classification, because we're doing sequence classification. Okay, so now this is like where we already differ slightly from the previous video. So we're going to load model. We're going to load the model. We're going to use the auto model for sequence classification because we're adding the last layer as a classification head. And we're going to specify like the number of labels is 3, like the number of labels. And we're going to add the quantization config to load it, the model and quantized. Okay, so let's run this. And then I'm going to show the model at the end. And remember, in the previous video, I had showed you how the model looks like. It has like this structure. This is like the coder only attention thing. And you see at the end, there's this like there's this thing here, which has basically like the big thing to notice as out features is 1, 2, 8, 5, 6, meaning that like you're doing text generation, and there's like this many different tokens. So like you can have any one of these as being the next one, right? But in our case, we're gonna do classification. We're gonna only have 3. It's gonna be bearish, bullish, or neutral. So you'll see that once we run this. So once it loads, you'll see the difference between the two. Again, this has this many, which is a ton. And then this, oh, wait, oops. And here, you see it has, look what it has. It has num features is 3, because this would be bearish, bullish, or neutral, the final thing we're going to predict. Okay, so now in order to use the parameter efficient fine tuning, we're going to have to do 2 steps. One is we're going to have to use something called prepare model for k-bit training. So this will be used to make the model be able to pre-process the quantized model for training. I guess I should read what I wrote. And then I just printed how it looks like. So as it, yeah, I printed how it looks like. Okay. So the next step is we want to like add the Lora. We want to make it like the model know that we're going to use Lora, right? So this is where you do get Peft model, and Lora config. We want to tell it about the Lora. Okay, so now this thing does a lot more interesting things. It'll add the Lora. Look at how where it adds the Lora things, the Lora components. These are the adapters. The adapters are like the things you're adding to the model when you're updating the weights for the fine tuning. Okay. So now that we're done that, we've loaded the model. We've told it we're gonna it's gonna be LoRa aware and QLoRA aware. Now we're gonna do the trainer thing. So like as I mentioned before, the main components of the trainer is you have to have like your model, of course, the tokenizer. You have all these training arguments, and then the data sets to train and the val data set, a data collator. Data collator will basically do like the padding, batching, handling special token, converting to tensors. It cleans things up a bit. And then you have compute metrics, which will basically log metrics all the time. And in our case, we're going to have a custom loss function because we're going to use class weights. So let me show you all these components one by one. So first, let's load the tokenizer, okay? So tokenizer looks like this. We're going to do auto tokenizer from pre-trained, same model name. And we're going to make the pad token be the end of sentence token. So let's see. Okay, so this is a tokenizer. Okay. The point is not to get into too much detail, just to show you guys how it works. But now we're going to set the model's pad token pad token ID to the tokenizer's token ID, and then we're gonna have to use cache equals false, otherwise it didn't work for me. Okay, so this is like the model part. Okay, so now let me just show you guys like how we have a model right now, but we haven't trained it yet. As you see here, it gave us a little bit of a warning. It said like some weights of llama for sequence classification were not initialized from the model checkpoint at meta whatever. So basically it means you should probably train this on a downstream task to use for prediction or inference. So we haven't done anything. But even though we haven't done anything, let me show you guys how we can get some predictions just to show you like how it looks ahead of time. So for our data set, we're going to go through the summaries. So let me just show you the first two. We have dftest.summary.toList, the first two. And then for the first two, we're going to show you how to make predictions. So to make predictions, we're going to have a few steps where you're going to basically, we're going to split the summaries into batches of size 32 for some speed and efficiency, but not too much because we don't want like a GPU error. So, so long story short, batch size is size 32, and we're going to loop through the sentences in batches, 32 at a time. We are going to convert the sentences to tensors with this tokenizer function. And return tensors is PT for PyTorch. We are going to have padding and truncation, and they're going to have a max length of 512. So basically this gives us tensors of size 512, PyTorch tensors because we did that. And then because these tensors are actually on the CPU, we're going to have to do this like thing here where we're going to basically do .CUDA to move it to the GPU. And then we're going to do this like torch no grad outputs equals model like this. We're going to, of the star inputs, this will give us like our predictions. And when we run this, and it'll take a little bit of time. So once it's done, now we have a list of tensors of size 32, which will have our prediction for the probability of labels 0, 1, or 2, which is bearish, bullish, or neutral. So let's concatenate it just to get one big list. So here it'll be the probabilities of each, or like the logits of each. And now we can do, of course, argmax to get the we can do the argmax to get the class. So we can do like this. Again, I'm just showing you this step by step, so like later you can play with it yourself. Yeah. So again, also this is just training doing the model, predicting with the model before even training. So now let's move to the CPU. So after we did the argmax, we move to the CPU because we want to convert it to NumPy. And set our predictions column of our data frame to that. For some reason, I got all ones, which is weird. I didn't get that in my practice things. Let's just see, just for the hell of it, how it looks like. Would be funny if this is all ones. No, it's not all ones, but it's mostly ones. Okay, so like now remember we had this like category map, which will like map the categories back. So let's map from the integers to the category. So now this will give it bearish, bullish, neutral, whatever. So I added this get performance metrics function, which is like the previous video, where you give it the data frame with the labels and predictions. It spits out a confusion matrix and a classification report and the balanced accuracy and the plain accuracy score. So let's see how that looks. I'm guessing this will be pretty bad. So yeah, it's pretty bad. Look, accuracy is 32 and 38. Okay, it's obviously much worse than what we had in the previous video, where we had started with we had 46 and 41, and obviously this looks a lot more nice. So now let's do the actual trainer. Okay, so we spoke a little bit about the training components needed. I said we're going to need this like tokenized data set. So let me show you how to do that. Okay, so basically with Hugging Face data sets, you have like this, you can have this map function, which will allow you to like apply a function to the data set. So like I did this here. What happens is I will apply the tokenizer to the summary column, and I'll use truncation equals true, max length equals 512. And then for the tokenized data set, it already applies the tokenizer. It'll also remove some extra columns we don't need anymore. And remember, I dropped the original label column, but now I'm going to rename the target column to label. So the target was the 0, 1, 2. I'm going to rename to label, and then I'm going to set the format to torch. We'll make another video on data sets. Okay, so remember I told you data collator thing. Actually, this step will be very easy because we did all the work in their tokenizer part. So it'll just be collate function equals data collator with padding. Okay, so now we have to define the metrics we want to use for evaluation. For simplicity, I'm just going to use balance accuracy and accuracy. So this is when you get this is for the valuation. When you get a val prediction, you get the predictions and labels. The predictions will be argmax axis is 1. Then we calculate the balance accuracy and the accuracy score. Okay, so now is where we do something a little bit interesting. We're going to define a custom trainer with class weights. So it's going to look something like this. The key thing is I should have written, we will have a custom loss function that deals with the class weights and have class weights as additional argument in constructor. So what I'm saying here is we add class weights to the constructor, we subclass from trainer, the Hugging Face trainer, and so we basically read the class weights, and what we do here is we're going to, the big picture is we have this custom loss. So with the loss is we're going to get the labels, and we're going to apply the inputs to our model, and we get outputs, and our labels are going to be the logits. And basically, I don't want to get into too much details, but the key here is we're just adding this part. The loss equals the cross entropy, and instead of just logits and labels, we add this weight thing, self.class weights. Okay, so this is the custom trainer. So now let's define the training arguments for the trainer. So this will be things like the output directory where we want to save it. I should call this I'll call this sentiment classification. And then things like the learning rate, the batch sizes, number of epochs, weight decay, all that good stuff. And the valuation and save strategy, like how often to save checkpoints, that sort of thing. So these are the training arguments. And then we define our custom trainer. So we'll have the model, the training arguments. I said the training data set is here. The tokenized data set accessing the train. The valuation data set accessing val. The tokenizer, the data collator function, collate fn, compute matrix, and the class weights we defined. So this was the trainer. And voila, now we can run the trainer. So this takes some time. The faster the GPU, the faster it takes. So we'll be back once it finishes, and we'll see if we got an improved model or not. Okay, so it's finished. We ran 2 epochs, but the validation loss seems to have gone up on the second epoch, which is just maybe a little bit of overfitting, or we should have lowered the learning rate. In full disclosure, I might have ran this more than once, which is the reason it looks like it's overfitting. But anyways, now that we have the model, the trained model, let's see how it does. I wrapped the previous steps above that made predictions. Like, remember we had the sentences. We converted it to a list of summaries. We split it into batches of size 32. We went through all those batches, and each one we tokenized them to tensors with batch size 32. We basically then moved it to GPU because they are on the not on the GPU, and we then of course made predictions by taking the outputs from the inputs, and then we added all the outputs together and concatenated it and set it to the prediction column. So this is what that did. So now it's running here, and once it finishes, we'll get the predictions, and then we are going to analyze the results. Where is that function that analyzes the results? It was the the get performance metrics. So let's hope that we at least beat this thing. Okay, great. So now let's get the performance metrics. Moment of truth. Okay, great. So our balanced accuracy score is 51.5. Accuracy score is 46. This looks a lot better. The confusion matrix, the precision recall, all that good stuff seems way better than before we trained. Of course, look, the precision was 0.17 here. Confusion matrix looks ridiculous, 30 in the 30s. But like, okay, let's compare it to like without fine-tuned the llama as is. What did that have? That had like 46 and 41% and smaller precision. So it even beats the llama model as is. So the fine-tuning definitely helps. Of course, this is assuming that like our actual labels are good and that sort of thing, which there's no guarantee that that is true. Okay, so now that we have this, we can save like the trainer state and model adapters. I'm not going to show you how to like load model for inference and that sort of thing in this video. We'll save that for another video because it's a source of a ton of confusion. But let me just show you how, saving the model. You can do trainer.save model, save model. You can also save the state of the trainer by doing the save state thing. And I saved a few more things. We'll talk about this in more details in the next video. Just real quick, the saved model is in this directory here. Has like the adapter model configs. This is like the additional weights we learned, tokenizers, special tokens, that sort of thing, the training params and that sort of thing. Remember we set the output directory to sentiment classification. So this sentiment classification is where it stores like our trainer states and that sort of thing. So we have our checkpoints and that sort of thing. So in the next video, I'll show you how to like upload this model and do inference. But for now, what we saw is basically like we were able to nicely beat the original model by fine tuning. So thanks, hope you enjoyed. If you're new, please like and subscribe, and see you in the next video. Thank you.